I am going to start with lecture slide set number 9. And I'm going to go over the very beginning of it, and I'm going to switch to lecture slide set 10. So this is kind of not really part of the lecture in the sense that it doesn't fit into what we've been studying. But for next week's lab, not this week's, next week's lab, we're going to need to know how to work with solutions and concentrations. So I just want to make sure it's clear, everybody's on the same page. So solutions, it's another word for a homogeneous mixture, or homogeneous if you like that pronunciation better. So for a liquid solution, actually any solution, but for a liquid solution in particular, there's going to be a solute. So the solute is the stuff you're dissolving into the liquid. That solute could be solid, liquid, or gas. Table salt, solid, another liquid like ethanol, alcohol, or a gas like carbon dioxide. For a liquid solution, the solvent is going to be a liquid. Often it's aqueous, meaning it's a water solution. Now, it doesn't have to be a liquid. For a liquid solution, it has to be a liquid, but you can have a solid in a solid solution. That's an alloy. A metal alloy is a solid in a solid, like steel. It's carbon, maybe some vanadium, maybe some other trace amounts of other metals dissolved in iron. That's a solution too. As long as it's homogeneous, it's technically a solution. We don't really call it a solution in common language, but that's really what it is. We're going to be dealing with liquid solutions. So the solute and solvent together are required to form the solution. So why are we talking about this? Well, we need these definitions to understand how to measure them. So, first of all, is that a solution? Shake your head. I'm not going to turn it on for this one. That's not a solution, right? There's no answer here. It has to be, at least visually, you see one thing, right? I see more than one thing. I see the liquid, I see the gunk floating in, and there's different kinds. There's the greenish, and then there's little black specks. That is heterogeneous, not a solution. So at a minimum, you cannot visibly distinguish the components, okay? And we saw in lab, even ones where you can't visibly distinguish them, even sometimes those aren't solutions, like the colloid solutions, where you have the nanoparticles that you can't see, but there's still little solid chunks floating around, and you can tell that they're there because of the light scattering, the laser. But anyway, and I won't turn the thing on for this one either, but when you dissolve salt in water, this is on exam of homework, what do you see, a physical or chemical change? Well, this is a physical change. So remember the difference between a chemical and physical change is in a chemical change, new particles are formed. Well, table salt, even though we write it as NaCl, and you might think, well, wait a minute, we're breaking these ions apart when this dissolves. Well, but we're not making new particles. This is just a formula that represents a giant block that looks like a bunch of NaCl's all stuck together. So in one dimension like this, but it's three-dimensional. So you just basically have a whole bunch of these ions that are just kind of neighbors. They're not, each of them is an ion. And when you dissolve this in water, all that happens is the ions are separated by a distance, but you're not making new particles. So dissolving this in water is just going to be a physical change. And you need to be able to understand this particle level picture. So here's sugar, and this is solid sugar over here, sucrose. When it's dissolved in water, the water molecules come in and start pulling apart the solid, but they don't break the particles. So there's still a whole sucrose molecule here. All that's happening are these sucrose molecules are getting separated and evenly distributed in this solution, in the solvent. And that happens the same with sodium chloride, table salt. We're not going to worry about the orientation of these molecules. That's a 222 thing. But these ions are being surrounded by water molecules, basically. And there's plenty of other water molecules just floating around, because usually in a solution, I didn't actually talk about this, but in a solution, how do you define which is the solute, which is the solvent? There's no magical, like water is always the solvent. It's technically the one you have the most of is going to be the solvent. So in an aqueous solution, usually we have a lot of the liquid water, and we have a little bit of salt, and we dissolve, and so that salt is the solute because we have a smaller amount of it. Okay. So drawing this particle level representation is something you should be able to do. So for something like sodium sulfate, first of all, this aqueous thing, this AQ, this is telling you that you have this salt, this ionic compound dissolved in water, aqueous. And so if it is like this, you shouldn't think of it as a solid. You shouldn't think of it as ions stuck together. You should think of it as a bunch of sodium ions and sulfate ions in a ratio of 2 to 1. So you can draw many more sodium ions, many more sulfate, as long as it's a 2 to 1 ratio. And these are all surrounded by water molecules. There's water surrounding everything. And then there's water floating around everywhere in between. That's the particle level picture of this thing. So if you see this in an equation, we're going to do over equations later on, don't think of it as its own little thing, self-contained thing. It's just a bunch of free-floating ions. That's what this means. You've just got a bunch of these floating around. And why does that matter? Well, sometimes we don't care about one of the ions. So sometimes we may not care about the sulfate. It's just there to balance out the charges. You know, we might only care about the metal part. So just keep that in mind. You just need to understand the particle level picture. So, concentration, when we measure these solutions, there are many, many, many forms of concentration. This is how much stuff is dissolved in the water, basically. The particular definition of concentration we're going to use is an amount of a solute divided by an amount of solution. So the denominator is not the solvent amount, it's the entire thing, the solution as a whole. There are versions of concentration where it's solvent in the denominator. If you've taken any biochem or anything like that, you might have heard of something called molality. And that has moles of solute over kilograms of solvent. We're not going to use that, but there's plenty of other ways to define this concentration. This is the one we're going to use. Solute over solution. And even then, those amounts, they're not defined by any particular units. You can use a mass over a mass, grams over grams. You can use volume over volume. You can use mass over volume. You can combine. And they have different meanings. You can do parts per million or parts per billion. So really what all this means, parts per million, is your numerator and denominator units are different by a factor of a million. So it's like micrograms of stuff over grams of solution. Excuse me. For parts per billion, it's nanograms of stuff over grams of solution. Okay. These are all different forms of concentration. You'll see in literature and anywhere you read about concentration. We're going to really focus on just one of these, molarity. So molarity is, we use the symbol capital M as the unit. Sometimes, we use this big M as the unit. If you wanted to define a concentration in an equation, like as a variable, it's often a C. Another way you'll see it is written in brackets. And what I mean by that is if you ever see something like NaCl with a square bracket around it, this stands for concentration of NaCl. So you'll see these in equations as well. Okay. But how you define the concentration in chemistry is often going to be molarity. Okay. So what is molarity? Molarity is moles of solute divided by liters of solution. That's it. That's the set definition. And I try to make people realize it as soon as you see anything written as molarity, with molarity. So for instance, if I were to give you this. So first of all, how would you say this? This is a 3 molar solution of NaCl, okay? And the annoying thing is that sounds a lot like moles, but it's different, okay? A 3 molar solution of NaCl. So that's how you'd say it. But the other thing I try to make people think is as soon as you see this unit, get rid of it. This big M is the same thing as writing moles per liter. So you can rewrite this as 3.0 moles per 1 liter. Always. That's a conversion factor now. So as soon as you see a concentration like this, it turns into a conversion factor between a liter of solution and moles of solute. So how would you make a 1 liter of a 1 molar solution of copper sulfate? How would you make 500 milliliters of a 1 molar solution of copper sulfate? What is the concentration if 3.184 grams of copper sulfate is dissolved in enough water to make 500 milliliters of solution? These are all really basic concentration problems that you should be able to answer. And again, the lab next week, you'll have to answer something briefly that has something like that. So for instance, how would you make 500 milliliters of a 1 molar solution of copper sulfate? Well, first of all, that 1 molar, translate that into moles per liter, 1 mole per liter. So if I have 500 milliliters, first of all, let's translate the 1 molar to 1 mole per liter. This is a conversion that converts liters into moles, or moles into liters, vice versa. Well, I've got a volume here, 500 milliliters. I'll convert that to liters. And notice that the units cancel out. Liters cancel out with liters. Numerator, denominator, and it gives me, this is an easy one, but it gives me, actually the wrong sig figs, here we go. 2 sig figs. Moles of copper sulfate. So the idea is, how would I make this solution? I would take 0.5 moles of copper sulfate and then add enough water to make a 500 milliliter solution. You might be thinking, well, what does this mean? How do I get 0.5 moles? We'll convert it to grams using a molar mass. So this next question, if I have 3.184 grams of copper sulfate, and I dissolve it in enough water to make a 500 milliliter solution, what concentration solution would I get? Well, again, concentration is moles per liter. I need to convert this into a moles amount, using a molar mass. I can get that from the periodic table. And sorry this is easy for you guys, but I know some people need the review. Copper is 63.546. Sulfur is 32.066, and then we have the 4 oxygens. So I have a molar mass of 159.61 grams for every 1 mole of that substance. So 3.184 divided by my molar mass is 0.01994. I've got 4 sig figs, so yeah, 4995. So that's how many moles of copper sulfate I have. I'm going to dissolve that. That's my solute. And I'm going to dissolve it in enough water to make 500 milliliters. So I'm going to divide this by the amount in liters. Divide 500 milliliters by 1,000, you get 0.5 liters. And that's your concentration. 0.039897, so 990. Big M. You could leave it as moles per liters too. That's fine. But it's the same thing as saying writing this big M. So that's the concentration of the solution. Notice that the wording, how they describe how you make the solution, it's not that they're dissolving it in 500 milliliters of water. they're dissolving it in enough water to make a 500 milliliter solution. Why is that? Well, if I put my copper sulfate in, that's like a lot, 3 grams, that's a little bit of a pile there. And then if I were to measure out 500 milliliters of water exactly, and then pour that in, together, the solute and the solvent actually might make a slightly higher volume than 500 milliliters. And so that's why it's worded the way it is. We actually have special equipment called volumetric flasks. They look like this. They have a long neck, and then they've got a big bulbous bottom that is flat, so it can stand by itself. But there's no markings on it except for this one line right up the top, here near the top of the neck here. And usually there's written on the side 500 milliliters or something like that. So the idea is you would put that 3.184 grams of copper sulfate in here first. You got your solid at the bottom, and then you'd add a little bit of water, just about that much, just to get it wet, and so you can mix it around and get it dissolved. And once it's fully dissolved, then you would keep adding water until you hit this line exactly. And then your total solution will be 500 milliliters, and it'll work with this, and you'll have the right concentration that you were shooting for. So actually, that's the exact thing we're going to do next week. We're going to make solutions that need to be a really perfect concentration. So that's how we do this. Any questions on this? I think we'll skip this for now, but if you want to try it, feel free. All right. So that's next week. I believe the pre-lab is going to have a question that has you calculate something like this. But you won't be able to calculate it until I give you the assignment. So I'll give you the actual thing you need to calculate in lab this week. All right. Okay. All right, hopefully that was all. I've seen this before. I just needed a reminder. All right, so hopefully we can finish up the shell model today. And then get to some more interesting things that we can learn, like atomic size. You might not think it's that interesting, but it is. It can be. And then periodic trends, so like the whole point of the periodic table. So this is kind of what we saw last week. We saw ionization data. So the ionization energy goes up, and then suddenly it drops, and then it goes up again, and then suddenly it drops. So we concluded that, the electrons must be arranged in shells, and as you keep adding more and more electrons, they'll fill up a shell, and then when they fill up that shell, you have to add the more electrons to a next shell, which is further away. And according to Coulomb's law, the further away the electron is, this denominator gets really big, because you have a large D. This whole term then gets smaller. The potential energy goes up. It gets closer to 0. It's the electron, this is not potential energy. This is ionization energy. The ionization energy goes down. It gets smaller. The electron gets easier and easier to ionize. How do you make sense of this table? So as you go across in a period, so from lithium to beryllium to boron, if you go across the periodic table, ionization energy goes up. Where's my little thing? There we go. Because, what is the explanation? Core charge. It's another thing we talked about last week. Okay. So people thought through, most people said B. And if you did say B, you'd be correct. So the reason as you go across a period, the ionization energy goes up is because, and if you want to talk about it in terms of core charge, the core charge increases, but the distance of that new electron, as you keep adding electrons, that electron doesn't change distance. It doesn't get further away. It stays the same. So remember what core charge is. Core charge is a way to just look at what a valence electron feels. So we're not looking at the electron and all of the protons and all of the, well, let me put it this way. We're combining all of the inner electrons and the nucleus together into one overall charge to see what that outer electron feels. So for instance, boron has a +3 core charge, and it's got 3 electrons, valence electrons. So this +3 core charge is the nucleus plus all the inner electrons, which is just 2 of them. That's boron. And as you go to the next element, carbon, it's got a +4 core charge, and it's got 4 valence electrons. And if you keep going over, carbon, you get to a higher core charge, more valence electrons, but the distance for these electrons to the center is not changing. You're adding electrons to the same shell. But when you go from neon to sodium, so neon in row 2 to sodium in row 3, the ionization energy suddenly drops. And that's why is that? These are great test questions. So, a little bit less agreement, but still overwhelmingly for D. So the core charge decreases, and the distance of the valence electron increases. And that's pretty much it. So if I'm doing the core charge model for neon, it's got a +8 core and 8 electrons. Don't forget the shortcut for core charge. It's the same as the number of valence electrons. Sodium has 1 valence electron, and so it's going to have a +1 core charge. But that valence electron is in shell 3, right? This is shell 3. This is shell 2. And shell 3 is further away, according to our model, from the nucleus. So this electron is both held on with a weaker core charge, and it's further away. So lower core charge, greater distance, okay? And that's why the ionization energy is so low. Or yeah, that's a good explanation for why it's so low. Okay. So, make sure you know how to do shell model and core charge model. We have a quiz this week, and I don't think we're going to do core charge. I think we're going to do the Bohr atom, like the energy level stuff. So finding the energy of a photon, the different distance from a transition, something like that. Okay, because this is kind of brand new. We just talked about it last week on Wednesday, and we need some time to fit it into our overall model. So we're not quite there yet. Okay. So again, the classic way to calculate core charge is the nuclear charge minus all of the inner electrons. So identify the valence electron, which is just this one. So everything else is an inner electron. So 19 minus 18 electrons. Okay. So you still need to know this. Even though we have this nice shortcut, it's the core charge is the same as valence electrons. It only works for neutral atoms. When we start seeing ions, you're going to have to do the original calculation, okay? All right. So in general, if you look at the periodic table, what's the trend in core charge as you go from left to right? Increase. It's okay, yeah. So, yes, everybody agrees. It increases, okay? This is a good thing to keep in your head, because when you look at the periodic table, it should be your like cheat sheet. It should be like, oh, I see exactly what's happening. So, there we go. So yeah, increases. And as you go from top to bottom, what happens to core charge in a single group? You follow lithium down to sodium, down to potassium, down to rubidium. Okay. Ooh, we got a little disagreement here. So, the core charge within a group, so just looking at one group at a time, the core charge actually stays the same. So, for lithium and sodium and potassium and rubidium, they're all +1 core charges. So the difference between them, then, is not the core charge. I mean, they're all the same. The difference between them is going to be their valence electron is in a shell that's further and further away as you go down. Right? So we just look at the distance of the electron from their nucleus at this point. I'm going to skip this one. As we travel from left to right across the period, the valence shell is the same as the core charge. Okay. Again, only for neutral atoms. So, what's going to take more energy? Removing an electron from a valence shell or removing an electron from an inner shell? Okay. Hopefully this is clear in everybody's head. Make sure. Yes, perfect. I've not failed you yet. All right. So, an inner shell electron is a lot harder to remove. All right. There's less in the way. They're closer to the positive charge. It's going to have a higher ionization energy, much harder to remove. This is why we don't really look at the inner shell electrons when we talk about reactivity. We only look at the valence shell. They're the furthest away, the easiest to remove. They're going to interact with the rest of the world, basically. They're more loosely held. And they are shielded from the nucleus by the inner electrons. So that's why they're easy to remove. So, what's the core charge of magnesium? No need to calculate it. Just look at the periodic table. Should give you an immediate answer. So not the atomic number. Let's see. Excellent. Somebody said 0. So it's neutral, that's for sure. But it has got a +2 core charge. So that +2 core charge is balanced out by the 2 valence electrons, okay? That's why it's got a 0 overall charge. But the core charge is +2. And the core charge is always positive because we're always doing nuclear charge minus the number of inner shell electrons, okay? You're never going to have more inner shell electrons, ever. So it's always going to come out positive, if it exists. All right. Okay, so what do you think will happen to the ionization energy as you move down a column, down a group? So I kind of talked about it, sort of. We mentioned it. As you go down a group, so look at lithium, sodium, potassium, rubidium, cesium. If the core charge stays the same, what else is different? Or what might affect that ionization energy? All right, we got some guesses. So it's somebody guessed D, but probably unknown, unsure. But it's a little split between A and B. So the answer here, what's going on? It's not there. But the answer is that the ionization energy is going to decrease as you go down a group. So why is that? Well, we talked about the core charge. They're all the same. For group 1, it's all +1, all the way down the group. But as we go from lithium to, for instance, cesium, number 55, the valence electron of cesium is in shell 5, which is really far away from the nucleus. Whereas the valence electron from lithium is in shell 2, which is going to be a lot closer to the nucleus. So just by distance, the cesium valence electron is going to be further away. According to Coulomb's law, is going to have a high potential energy, close to 0. So it's going to have a very small ionization energy. Right? Cesium is going to have a very, very low ionization energy compared to something like lithium. And actually, we see this in real life. If you've ever watched the alkali metals explode in water, there's like a demo on YouTube that shows this, and I'll probably look it up in a second. It'll show you lithium. Plop a piece of lithium in water, and it fizzes, and it's, it gets a little violet, but that's all it does. Sodium starts popping a lot more. You can see it catching on fire a little bit. Potassium starts to explode when you hit it with water. Rubidium is more violent, and cesium is so violent it breaks the container. As soon as you put a little tiny piece in it, it breaks the container open. Like there's a big tub of water, or a glass tub of water, and it breaks the glass immediately. Yeah.
Just to be clear, the ionization energy is the energy required to remove an electron?
Right.
Okay.
So if the ionization energy for cesium is super low, then it's really easy to remove that electron, meaning it's super reactive.
Okay.
Here, wait, I don't know if we've seen it yet. I think I showed somebody, but yeah, let's pull it up. Come on, Slowpoke. Yeah, this one's a good one, I think. Unless somebody just...
So I've got my essay written, and I've been working on it for about a week. So now I'm going to show you how I use Grammarly to edit.
There are 6 alkali metals: lithium, sodium, potassium, rubidium, cesium, and francium. They're all soft metals which can be cut with a knife. In air, the elements quickly become coated with compounds that form on the metal's surface. Here, for example, is lithium. When we slice it, you can see the metallic luster, but the black coating quickly reappears.
What they're showing is
Sodium is kept under oil to prevent reaction with air. Again, when we cut it, the metal surface can be seen. But this time, corrosion occurs even more quickly. With the next alkali metal, potassium, the corrosion in air is so quick that it's hard to see the metallic luster at all. As we go down with it, giving off hydrogen, half the gas is produced, and the metal dissolves to give an aqueous cation with a single positive charge.
There's one that shows all of them in a row. This one.
Now let's see another reaction. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a lilac flame. The next element is rubidium. This time, we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our 5th alkali metal.
That's easy. So, I wish they were labeled. But yeah, so lithium just kind of fizzed. Sodium was a little more violent. Potassium, more. Yeah. So we know why. It's
Group 1 of the periodic table is...
understand why they're different and why these are more reactive now. What about across a period? So if you go across a period, what happens to ionization energy? So across a row, do the ionization energies increase or decrease? This one's a lot easier, I think. Yeah. Okay, so most people saying increase, yeah. So it definitely increases. You can just go by core charge, right? Sodium is a +1 core charge, magnesium +2, aluminum +3, silicon +4. As you get to argon, it's +8. And that core charge is literally what kind of charge does that valence electron feel from the core, from the combination of the nucleus plus the inner electrons. And the higher the charge, the higher the ionization energy is going to be. The more attracted it is and the harder it is to remove. So here's the ionization energy laid out in the periodic table. This is labeled IE1. So that 1, that subscript on ionization energy, indicates the first ionization energy. So we're removing the first electron. Because of course, most of these elements have multiple electrons, and you can keep removing electrons. So we're only talking about removing that first electron. That's what that 1 means. And you can look at the trends as you go across a row. Ionization energy kind of goes up. It's not perfect, but it goes up. And then as you go down a group, ionization energy drops. And that even holds for the noble gases. They have much, much higher ionization energies than the alkali metals do, but they still drop. And that's because that valence electron, even though they're all feeling that +8 core charge, they're further away. So technically they're easier to remove. Okay. Because of this identical core charge in a group, elements in a group tend to have similar reactivity, similar properties. That's why the alkali metals are called the alkali metals. That's why the halogens are the halogens and the noble gases are the noble gases. Okay, there's a method to the reason. There's a reason the periodic table is arranged this way. Okay. So this is just a summary of what we understood. Each row, remember, is a new shell. Yeah, this is all this, we've talked about this. And we've covered this. I think we did this at the very end of class last week. So, so let's kind of dive a little bit more deeply into the patterns of the periodic table. You can understand a lot of stuff about the elements just by looking at the core charge and the valence shell. Okay. So, to understand a little bit more deeply, to kind of understand, for instance, let me go back real quick. You know, why might there be differences between nitrogen and oxygen? Why might there be a difference between beryllium and boron? So beryllium is actually a higher ionization energy than boron is. You know, so why is there a big separation between this part of the periodic table and that part of the periodic table? Okay, there's a reason why, but why might that be? So we're going to look at a little bit more data. So instead of just the first ionization energies, we're going to look at extra ionization energies, the second one, the third one, and even higher. If I start removing multiple electrons from an atom, what kind of energies do I see? So again, second ionization energy is the energy required to remove a second electron. So you start with a cation, for instance, sodium plus, and I strip a second electron away to make it sodium 2 plus. So there's the first ionization energy for sodium, removing 1 electron from a neutral atom to make sodium plus. And then if I do it again, that's the second ionization energy. Notice the difference. Almost 10 times as much energy required. So the total ionization energy, or the total energy required to make sodium 2 plus is this whopping 5,000 kilojoules per mole of energy. Okay, so here is the graph that kind of shows you these different ionization energies. And we're kind of look at some of the trends, just kind of understand what we're seeing here. So First of all, you can see that between sodium, the first ionization energy and the second one, there's a giant, like a big difference, almost 10 times as much energy required. If you look at the next element in the same period, magnesium, to remove one electron, it takes a pretty sizable amount of energy. To remove a second electron, it takes even more. So first of all, remember, why is this ionization energy higher than this one? Because magnesium is a +2 core charge, right? The higher the core charge, the higher the ionization energy is going to be. To remove a second electron, it takes almost double the energy. Okay, why might that be?
Because there's two electrons in the valence or the outer shell.
Well, now so when you go from here to here, there's only one left. And so here, there may have been electron-electron repulsion that helped keep this low, but now there's only one electron left in that valence shell. So less electron-electron repulsion, more attraction with the nucleus. So that's why it's higher. But then when you try to remove a third electron, it skyrockets. Like it's not just double, it's like 5 times as much. So what we're looking for here is a big jump in energy. So here, from here to here, you know, maybe triple, something like that. Here, it not quite doubles. So we're removing one electron, removing a second electron, removing a third electron. But removing a fourth electron for aluminum you can see that that's a massive jump in energy. Same thing with silicon. First electron, second electron, third electron, fourth electron. To remove that fifth electron, it's a huge jump in energy. And that stair step, that giant jump in energy, kind of repeats just with the next electron for every subsequent element. So all we're doing is looking at all the different elements in the same period. So that's the pattern we see. You know, why is that? Why is it so big? So why is the second electron require so much more energy for sodium?
Because it's on the inner shell.
It's an inner shell electron. So here we're removing the valence electron. There's only one valence electron. It takes some energy, but it's easier. Here we're removing an inner shell electron. Magnesium has 2 valence electrons. They're relatively easy to remove. The third electron would be coming from an inner shell. Aluminum has 3 valence electrons. That's the inner shell electron. Silicon has 4 valence electrons. That fifth one is the inner electron. So that's further proof that this shell model thing exists. Or the concept of shells is a valid way to model the atom, let's put it that way. It's a more accurate statement. So, just looking at ionization energies, which element in this period 3 would fit this data here? Oh, I should turn that clicker on. There you go. So we have choices A, B, C, D, and E. Just looking at this data, which would make sense? Which element would this be? So here's how you should think about it, okay? So 3 voted for D out of the 5. So here's how you should think about it. You should look at the energies and say, okay, well, it's high, but is this to this a lot higher? You can just look at the pattern. You know, it's going up, it's going up, it's going up, it's going up. That's expected. But here, the jump is so much higher than before. You know, it doesn't double, it like quadruples or something like that. That's a big difference from what happened before. So that is most likely an inner electron. The 6th electron is an inner electron, meaning the first 5 are valence electrons. This thing has 5 valence electrons. So which element from period 3 has 5 valence electrons? It's 1, 2, 3, 4, 5. It's the phosphorus. Okay? So in this case, it is D. Which I think, yeah, everybody changed their answers. It's fine. So that's how you should look at this data, okay? All right. So besides ionization energy, we're going to look at things like atomic size. Just kind of explain away what's happening there. Now there's two ways to kind of think about size. One is just a pure atomic size. And the trouble with kind of figuring out the size of an atom is where do you just define as the end point of the atom? So I'm going to spoil things already a little bit, but you know, this model is too simple, like having the electrons orbit the atom. The real picture of what the electrons are doing is they're just kind of flying in a certain volume around the atom. And we think in terms of probability when we talk about where the electron is. What is the likelihood of finding it out here? You know, 90%, or is it much, much lower? So as scientists, we create a cutoff. We say, okay, well, we're only going to include, you know, 90% chance of finding the electron. That's it. Anything less than that, we're going to just say the electron is going to be not very likely to be found. And that's how we kind of define how big an atom is. But that's kind of a nebulous definition. So a lot of ways we can define the size of an atom is by looking at how much space it takes up in a solid or in a bond or something like that. So this is one way. Take a metallic radius. So you've got a whole bunch of atoms stuck together in a big solid piece of metal. What you can do is you can measure the distance between the center of two atoms and then divide that by 2, and that's the radius of your atom. That's the metallic radius. We can do ionic radii that way, but that's different because we're talking about ions. Here we want the neutral atom size, okay? The other way to do it, if you can't have a metal, for instance, what about covalent stuff? You know, most of these things like fluorine, it naturally comes as F2. It doesn't exist as F atoms by itself. And so a covalent radii is another way to define the radius of an atom. So you measure the distance between those two atoms that are making a bond, and divide that by half. It's different than this because these are actually sharing electrons, so they're a little closer than they normally be. But like I said, it's very difficult to precisely define how big an atom is. So there's lots of ways to do it. These are two, okay? And so, you know, once you measure a Cl-Cl bond and you figure out the size of a Cl atom from that bond, you can then use it in other bonds. So for instance, you have a C-Cl bond, a carbon and chlorine bond. Well, I can measure the distance between those two, 177 picometers. I've already figured out that chlorines are on average 100 picometers across. So I can subtract that from this side, and then now that I can figure out, oh, the carbon is about 77 picometers. It's not the best way to do it, but that's one way to do it. So that's how we measure size. But you know, really what we care about is predicting size, relative size, not the exact size, but just understanding what's bigger. So if I go down a column in the periodic table, would I expect things to get bigger or smaller? This is the easier one of the two. We're going to do the across too. But if you go down a group, do atoms get bigger or smaller? All right. Everybody says they get bigger. Perfect. That's what you'd expect. Why? Because we're adding electrons to a shell that is further away. So if you define the atoms by how far the electrons go, the further down you go, cesium has electrons in shell 6, which could be further away than shell 5 electrons and so forth. So increase is, yeah, the answer. What about when we go across? If I go from sodium across to argon, for instance, Na to Ar, would you expect the size to get bigger or get smaller? All right. So competing answers. Anybody want to suggest a reason why they think that they're right? Yeah, what do you think?
Because we add protons into the nucleus of the atom.
Okay, and then what does that do?
It increases the
you are close to the answer, but you have it a little backwards. So you do add more protons. Yeah, you want to say?
So having the more protons, the electrons are attracted to it more, which pulls it tighter.
Yeah, that's it. So we know that as we go across a period, we're just adding electrons to the same shell. But we're also getting a bigger core charge. And so, yeah, what that core charge is doing is it's making the shells a little bit smaller. It's pulling those electrons a little bit closer because of the size, because of the attraction, the charge attraction there. So, yeah, as you go from sodium to argon, they do get smaller. So it's a little bit counterintuitive. You're adding more things, but it's shrinking it because they're all going to the same shell. So there you go. There's a picture. As we predicted, as you go down a group, it gets bigger. And that's pretty much true for every group. It's not perfect. Again, these are trends, not a rule. They're just trends. But left to right gets smaller. And actually, that's a pretty good trend compared to ionization energy, which is a little bit harder to match up. Although there's a little bit of a blip there. But mostly it's good. There's another one down here too. But it's mostly good. Okay. So, why, again, we're getting new shells as we go down a group. But then as we go across a period, we have the same shell, just have a higher core charge, which is pulling everything a little bit tighter. All right, so now let's add ions to the mix. What happens when we start doing ions? So, if I take oxygen, the atom oxygen, which doesn't exist by itself normally, and I add electrons to it to make O2 minus, the radius increases, it gets bigger. So why would it get bigger? Well, more electrons, more electron-electron repulsion. That's the simplest explanation. So the more electron-electron repulsion, the more they can kind of repel each other away from the nucleus and just kind of make the atom overall slightly bigger. If I remove electrons, the radius decreases. So for instance, if I take sodium and remove its one electron. So why is that? Well, there's also the same reasoning. If I remove electrons, there's less electron-electron repulsion. But in the case of sodium, it's even a bigger reason. Let's see. Hold on a second. Well, okay, we'll get to that in a second. But, here, let's just look at it here. So here's sodium. If I remove this electron, and we say that the size of the atom is defined by how far out the electrons go, well, I don't have electrons in shell 3 anymore. So the furthest out electrons I have are the shell 2 electrons now, which are closer to the atom. So for sodium, when I make it sodium plus, not only are there fewer electrons, so fewer electron-electron repulsion, but I've actually drastically reduced the size because now I don't have electrons in the shell 3 anymore. My valence shell is now shell 2, which are much closer to the nucleus than shell 3 electrons were. Now, when we compare these different charges, we have to compare like atoms, okay? It's too difficult to compare different atoms, neutral versus charge or something like that, okay? There's an exception to that, but we'll get to that. So we're going to mostly compare like atoms, okay? So, which has a larger radius, Mg or Mg2+, which is bigger. These are also good test questions, really quick, easy, not easy, but you know, something you should be able to answer at some point. All right, most people put it A, and it is A. The bigger radius is going to be magnesium because it's got 2 valence electrons in shell 3. But once you remove those 2 electrons, once you have that magnesium 2+, then your outer electrons are in shell 2. which is a smaller shell. So Mg, the original metal, is bigger than the cation, than Mg2+. Okay. All right, what about Cl versus Cl minus? Which is bigger? All right, this will be easy. Oh, we got a few differences of opinion here. The bigger one in this case is going to be, clear this out of the way, come on. It's going to be B. The difference between them, they both have 17 protons. Chlorine has 17 electrons, Cl minus chloride has 18 electrons, but that extra electron is going into the same shell. So shell-wise, they're about the same. So the only thing the only thing we could kind of talk about that makes a difference between them is just slightly more electrons. Means you'll have more electron-electron repulsion, which makes it slightly bigger. So Cl minus is slightly bigger. Okay. Okay. And here is a nice little chart that shows the neutral atom versus the ion. Here you've got the halogens and their approximate size, covalent radius. I believe this is in P. Oh, sorry, radius over here, nanometers. And then this is the row that they're in. As soon as you add an electron to them, they get bigger. And it's a pretty consistent increase. For the cations, for the metals are all bigger than the cation form. Because as soon as you take an electron away, they shrink inside. And yes, it's less electron-electron repulsion, but a bigger effect is the fact that their valence electrons are now a shell below, right? In a lower shell, which makes it just a drastically smaller atom. Okay, so anions are bigger than their neutral form. Cations are smaller than their neutral form. If you like to memorize trends, that's one way to do it. But I think understanding why is a better way to learn this. And here's a nice little graphic that shows you the neutral form versus the cation or anion. So on the right side we have the neutral. On the left side we have the ion form. And you can see that the cations are universally smaller. In some cases, drastically smaller. Look at the boron versus boron 3+. And then the anion is always bigger than the neutral form. So sulfur versus S2-. Doesn't even fit on the chart. They had to cut out a section on the top and the bottom. Okay. All right. You might be thinking, oh, yeah, that makes sense. Well, now that you know this, and you can think about this in terms of shells, yes, it should make sense. Oh, there was the video link. I could have just clicked on it there. So, we have sodium metals in water. Here, this is a nice one, just for fun. Can't do this in class. It would be a little bit too much.
Grammarly does more than catch errors. With Grammarly, you can find really good, no, perfect words.
Okay. The sodium toilet, that's just, you guys can watch it. Anyway, So why do the elements in the same group react similarly? It's because they have the same valence electrons. It's because they have the same general core charge. There's slight differences between them. The distance, where the electron is compared to its nucleus does have an effect on their reactivity. But overall, they have similar reactivities because of that valence electron. Okay, so let's talk about something new. A new term is isoelectronic. So when something is isoelectronic, we say that it has the same number of electrons. That's really what it is. You can kind of take it a step further if you need to. And we haven't talked about electron configuration yet. But essentially, they also have the same electron configuration. We'll get to that later. But same number of electrons is really the key here. And the idea here is these atoms and ions are isoelectronic, meaning they have the same number of electrons. So O2 minus has 10 electrons. F minus has 10 electrons. Neon has 10 electrons. Sodium plus has 10 electrons. And you can count these out. So the protons are all different. That's what makes them different elements. But in this case, they all have 10 electrons. So this is the first one we're going to do from the workbook. Chem Activity 6, page 137, 139. Let's go through questions 6 through 13. Give you a break from my talking. And let's kind of absorb this new thing. Come on. 137, 139. Where are we? There we go. These are the hardest to kind of think about and figure out trends and relationships. So to make sure that this is sinks in a little bit. Hopefully people had some time to think about this. So you saw some weird core charges in that table, really large ones. So they all have 18 electrons. Argon is the neutral atom that is isoelectronic with those ions in that table. And here is potassium plus. So I don't know if you've noticed, but I didn't draw the fourth shell because normally potassium would have 1 electron in its fourth shell. That's regular potassium. Potassium plus is missing 1 electron, and so that last electron is not there. So there's no need to draw the fourth shell. That's not the valence shell anymore. The valence shell is now the third shell, and so these 8 electrons are technically the valence electrons now. So when I calculate the core charge, it's 19 protons minus the inner electrons. So just these 2 and these 8 together from shell 2 and 1. So 10 electrons. Those are inner electrons only. So 19 minus 10 is a plus 9 core charge. That's how they get that number, that really large core charge. So what is the basis for the trend in ionic radii in table 2? Well, this trend is showing the radius going down. It's getting smaller. So how do we explain that trend? Well, you can just look at the core charge and see. The larger that core charge is, the more attracted the remaining valence electrons are. So, you know, these electrons, valence electrons being held on with a +6 core charge, they're going to be, you know, so attracted to the nucleus. But if the core charge increases to +10, then those valence electrons are going to be more attracted, pulled tighter, closer to the nucleus. And that's why the atom sizes get smaller. So this is different than looking at the periodic table and understanding, you know, where the size is, because we're talking about different charges now. These are all isoelectronic, but different charges to each other even. So you have to think about it in a different way. Next. Predict which is larger, the O2 minus ion or the F minus ion. Well, O2 minus versus F minus, why those? Well, F minus is F minus would be the ion formed from fluorine, O2 minus would be the ion formed from oxygen. Those are just one period up from S2 minus and Cl minus. And, you know, if the trend fits, S2 minus and Cl minus, they have a core charge of +6 and +7 respectively. Fluorine and oxygen should be the same way. They should operate the same way. So fluoride, F minus, should be smaller than O2 minus. Why? Because F minus should have a +7 core charge. Yeah, if I'm thinking about this right. And O2 minus should have a +6 core charge. So, which is bigger? The O2 minus should be bigger. For the same reason, the S2 minus is bigger. Okay. All right. So shell model diagram for F minus. So drawing these shell models, this is a good thing, a good skill to be able to do. You're probably going to have to do it on a quiz next week. Definitely going to have to do it on a future test. So F minus, we have 9 protons in the nucleus. We have our first shell with 2 electrons. And our second shell, instead of having normally 7 electrons, it's going to have an extra one. 1, 2, 3, 4, 5, 6, 7, 8. There's the 8th extra one. So that's F minus. And what is the core charge going to be? Well, the core charge is 9 protons minus the inner electrons. Just 2. So +7 core charge. Did I do that right? Yeah, okay. Yeah, there it is right there. Okay. So F and F minus have identical core charges, and the valence shell is n equal to 2 in both cases. Explain why the radius of F minus is larger than the radius of F. Okay, well, we already know this one. But if they have the same core charge, the valence shell is the same, everything is the same except F minus has an extra electron. Well, why is it bigger? It's the extra electron. It's the extra electron-electron repulsion. That's it. The only reason why it's bigger. So electron-electron repulsion is the reasoning. What is the radius of N3 minus? Explain your reasoning. Anybody know? What's a good prediction for N3 minus? Well, you can see F minus. You can see O2 minus, it's bigger. N3 minus is probably going to be bigger if you follow if this is a trend. So N3 minus should be bigger. Why? N3 minus is going to have a +5 core charge, and it's going to have 8 electrons. So with a +5 core charge and 8 electrons just like these do, with a +5 core charge, those electrons should be further away. They're not held on as tightly. Okay, so far so good? So, understanding the trends for these isoelectronic elements is a little bit trickier. You probably can find a pattern, you can memorize the pattern, but understanding at its root why they're different, how to predict it just by looking at a shell model is a good thing to be able to do as well. So we've answered this one, which has a larger radius. It's the O2 minus. Honestly, the way I like to think about it is if they're isoelectronic, that means they have the same number of electrons. Well, if they have the same number of electrons, then the shell model is going to look the same, except for the protons. So then you look at the protons. Whichever one has the most protons is going to be the smallest. The one that has the fewest protons is going to be the biggest. So which is going to be the biggest? It's going to be the one with the fewest protons. Oxygen has fewer protons than fluorine. All right. This argument, again, only works if you know that they're isoelectronic. If you know they have the same number of electrons. And you can count. So there you go. Oxygen has 8 protons only. So out of these three, which has the largest radius? Which is the biggest? See. All right, most people say A. One person said D. And the answer here is A. So, the one thing I would caution you is make sure that they're isoelectronic. Make sure that you're comparing apples to apples. So, for one of these, aluminum 3+ actually has a lot fewer electrons than these do. Okay, yeah, it's in the same period, but you're actually taking away electrons. So this actually has 10 electrons. These all have 18 electrons. A completely different ballpark. This is going to be the smallest just because of that. But then once you get rid of this one and you compare these three, the one with the fewer protons is going to be the biggest, and that's the phosphorus one. So double check that they're isoelectronic first. If they're not, then sort them into groups and compare the groups first. Make sure you know which group is biggest or smallest, and then once you hit, then you can sort within the groups. Okay. All right, now here's the interesting stuff. So, my phone just keeps going. We talked about ionization energies and kind of done what we can do with those basic experiments. Ionization energy measurement is pretty crude, I guess. Not crude, but it's like really simple. You're just throwing energy in an atom and just trying to see the first electron that comes out. What is its energy and where did it come from based on that? So we're going to now use a more sophisticated technique to probe the energies of the electrons in an atom. We're going to use something called photoelectron spectroscopy. And this is an interesting technique because what it does is it zaps atoms with X-rays. And the X-ray energies are just like huge. They can be gigantic. Meaning you can start to remove electrons from the core before you remove valence electrons. You can remove any electron you want using photoelectron spectroscopy. So yeah, we're using light, generally X-rays. And as long as we know the energy of the light, the light that hits the atom, the photon hits the atom, we use that energy to calculate the ionization energy based on how fast the electron that comes out is moving. So the photon that we hit the atom with is always the same energy photon. It's one wavelength, one energy. Right? That's this energy here. Now the electrons that come out, some of them are coming out moving quickly, some of them are coming out moving slowly. And the idea is the more quickly the electrons are moving, the higher the kinetic energy, the less energy it took to ionize them. And the slower they're moving, when the ones that come out, if they're moving very slowly, that means it took a lot of energy to ionize them. Most of the energy of the photon went to ionizing it, and only a little bit was left to make the electron move quickly. So we're talking about conservation of energy, where the photons have a set amount of energy. It's plenty of energy to ionize it, but there's going to be energy left over that causes the electron to come out with a certain amount of velocity, a certain amount of speed, a certain amount of kinetic energy. And the more energy, the faster they're moving, that means it took very little energy to remove them. So, we kind of measure it like this. You have a beam of atoms. What does that mean? It means you've got this source that's heating up your atoms into a gas form. We're directing the gas stream of atoms in one direction. That's this beam of atoms. So you've got atoms coming this way. We're shooting them with photons going that way. And then sometimes electrons will come out. And they'll come out in all directions, but we can kind of analyze in one direction. These electrons, are negatively charged. And just like the mass spectrometer, we can use magnetic fields to kind of make the electron bend a certain way. And we can control the strength of the magnetic field. The faster the electrons go, the more magnetic field we need to get them to bend before they hit the wall. The slower they are, if we use too much of a field, they'll hit the inner wall. So we know how fast they're going by what kind of magnetic field strength we need to set the machine so that they hit the detector. All right, that's the basic photoelectron spectroscopy setup. I'll show you the video, maybe. Well, we'll see. It's not a very interesting video. These experimental setups are just basically these giant blocks of metal with a lot of wires sticking in them. You don't see much. You just see a computer screen that reads a signal. It's not much to see. Anyway, here's the basic setup again. So before we get into the setup, I want to remind you, for the same atom, to have any atom, the ionization energy of the inner shell electron is what compared to the outer shell electron? All right. Still get somebody going backwards a little bit, but for the inner shell electron, the inner shell electron's ionization energy is always going to be larger. It's harder to remove inner shell electrons, and so they have a higher ionization energy. The outer shell electrons are easier to remove. They have a lower ionization energy. But it doesn't matter. Photoelectron spectroscopy can eject any electron. Okay, we're no longer limited to the valence electrons. So here's chemactivity 8. We're skipping all the way now to 8. We've finished our basic shell model. We're going to refine the shell model now using this information. So here is a sample energy of photons. So 143.4 megajoules per mole of photons. Those are really high energy photons, okay? Those are X-ray photons. All of that energy hits the atom, and a certain electron is going to come out, either an inner shell electron or a valence or any combination of them. And that electron is going to have a certain velocity. So in this case, they're saying that the energy of the electron, the kinetic energy, is 114.8 megajoules per mole. So let's see if we can understand what we're seeing. This is kind of a standard photoelectron spectra of what you'll see, and these is perfect data, and they don't look this nice always. So for a hypothetical atom that you saw here, where you have one electron coming off, that's what we would see. Like, we would see a peak. That peak would correspond to a certain ionization energy. All right, you would use this kinetic energy and the photon energy together to calculate the ionization energy. There it is. Photon energy and the kinetic energy, a subtraction gives you that ionization energy. And on the y-axis, all we see is something called relative number of electrons. This is basically the signal from the detector. The detector is going to see a constant stream of beep, 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 you know, when you get the right energy. But it's not going to be able to count precisely this number of electrons per atom. All right, it's just going to give us a signal. That's it. So let's start off with questions 3 through 8. So we're skipping all the way ahead to page 167. Let's start off with this stuff. This makes sense. We're going to see spectra that get exceedingly more complicated, so make sure they make sense in the beginning. Yeah. So they're saying that the result is the calculated ionization energy of 28.6. So this is from this particular fake atom. Okay. So we hit it with this much energy, right? That's the photon energy. an energy that it took to ionize it, which is this. And where'd the rest of the energy go? The rest of the energy went to making the electron move quickly, which has this kinetic energy. So just verify that it makes sense, which means, make sure that these numbers fit that equation.
Oh,
Does that make sense?
I see, okay.
Yeah. Yeah, so number 3, you're just making sure that the number makes sense. That's it. Fits the equation. I don't know if the schedule's out yet either, but I am teaching 222 at the same time as this one. I think it's the same time. Maybe it's like half an hour offset, but they might change that. And if you don't like this time, there's a Tuesday, Thursday version too. And if you want to take it with me, that's fine. I'm not offended. Everybody has their own styles of teaching they prefer. I don't know how far you've gotten. I don't want to run out of too much time. I want to get through a little bit so that we can have this started and finish it on Wednesday. But number 3 is just basically verifying that this 28.6 megajoules per mole makes sense. So as I was saying, this is this model, this fake atom. We hit it with energy, photon energy that has this energy. That's the total amount of energy we hit it with. Where does the energy go? Well, some of it goes to ionize the electron. That's what that number that they said in the problem was it 26 point something? Was it 28.6, excuse me. So what I mean by that is the energy of the photon was 143.4 megajoules per mole. Some of that went to ionize the photon. The rest of it went to make the electron move very, very quickly away from the atom. The kinetic energy is the energy of motion, okay? So the electron is really fast now. It's speeding off with an energy of 114.8 megajoules per mole. These two sides should equal each other. And they do. Okay, yeah, they do. So the machine is technically reading the kinetic energy of the electron. That's what the machine is doing. But it's automatically converting that using the photon energy, because that's what the laser that the machine's using, and it translates it to an ionization energy using this very basic equation. So that's what that peak is. The energy right here, this little hash mark, is that 28.6 megajoules per mole. So if you had to label it on the x-axis, 28.6 megajoules per mole is right there. Okay, so what determines the position of each peak? Where on the horizontal axis? It's going to be the ionization energy, okay? Which is the value of the energy level for the electron that is represented by that peak. So the energy level, the potential energy, what is going to be? Positive or negative? So the electron that we removed, you needed 28.6 megajoules per mole of energy to remove it. That means that, where was that electron? It was sitting in some energy level that was at negative 28.6 megajoules per mole. We're used to seeing regular joules. Megajoules per mole is just, scaled up more atoms, but it's the same idea. So that electron was at a potential energy of negative 28.6 megajoules per mole. We hit it with that much energy, and that ionized it, brought the potential energy to 0, and the rest of the energy went to speeding it up. That's where that total energy was. What determines the height or intensity of each peak? So this is, again, a little bit more kind of difficult to think. But this machine is just getting a signal. It's like the electron is hitting the detector and it makes a click. It registers as, hey, something hit me with this particular amount of energy. And the more atoms, the more electrons you generate from the more atoms, you're just going to get more signal. So this height just represents the proportion, the number of electrons that you're seeing hitting the detector. It's not the number of electrons per atom, because this is not one atom. We're hitting that millions of atoms. So this is just all the electrons from all those atoms. They're all giving us the same energy. So it's just a total number of electrons from all the different atoms. Okay? That's it. There's nothing more specific about it. And then 8, why is it not possible to determine the number of electrons in an individual atom? So basically what I just said. The experimental setup, we don't just inject one atom, hit it, and then see what electron comes out. We're constantly getting electrons, a stream of atoms going through the detector, going through the machine, and we're hitting it with tons of photons, and every atom is going to have a different electron come off, or maybe the same one, but we can't really count individual atoms. We're just getting a whole bunch of signal from these electrons. So that peak just means we have electrons at that energy. We don't know how many electrons. It's not 1, it's not 2, we don't know. We can't tell how many per atom. So, we're done with that. So let's envision a more complicated atom. And this atom has 5 electrons in it, and they're at 2 different energy levels. We have 2 electrons at a very low energy level, very negative, and then we have 3 electrons at a slightly higher energy level. So what might, let's answer the question, but basically you're going to kind of come up with what might you see in a photoelectron spectrum from this hypothetical atom. So let's try 9 through 11 real quick. Give you a chance to kind of think about it. clock's a little fast, so we got a tiny bit of time left. 5 minutes. All right. I'm sorry if I'm cutting you off a little short, but let's go over these questions really quickly. Not really quickly. Let's finish up the class with these. Number 9. How many peaks will you see? How many do we think? Just 2. So you can either remove one of these electrons, which cost that much energy to remove. That's the ionization energy you need. Or you can remove one of these 2 electrons, which cost a little bit more ionization energy. Right? Remember, ionization energy is the amount of energy you need to bring those potential energies back to 0. So you've got 2 ionization energies. So you'll see 2 peaks. What about the relative height of the peaks? So I know that the last example, we can't count directly how many electrons are in an atom. But if I have 2 different peaks, I should be able to see a ratio, a proportion. And there are 3 electrons at this energy level versus 2 electrons at this energy level. So if I hit enough atoms with photons, I should start to see a distribution of 3 to 2. I'm 3 times more likely, let's put it this way, I'm 1.5 times more likely to see this energy than this energy, right? Because there's 3 electrons versus 2 electrons here. So if I do this enough times, I should see a slightly bigger peak for this energy and a slightly smaller peak for this energy because of just the proportion of electrons I have. So relative height, I should see like a 3 to 2, basically, ratio. Just based on the number of electrons there are. So now that we have those 2 things out of the way, we should see 2 peaks, right? One for this energy level, one for this energy level. And I should see a ratio of about 3 to 2 because of the number of electrons. What is my graph going to look like? Well, you wouldn't know this, but one of the quirks of photoelectron spectroscopy is that on the x-axis, the ionization energy goes backwards. It's a quirk that, I don't know who started it, but that's how it's always been done. So we put the smaller numbers to the right, okay? That's just what you'll see. So 0 is over here, of course. Nothing's at 0. And you'll never see it, usually. It starts at some number. But the 2 energies you see are, well, the energy levels are minus 0.85 and minus 4.25. So the more negative one, this is the minus 4.25. Right? That's this energy. And this energy, they're not very proportional, but is minus 0.85. So what are the ionization energies going to be? The opposite. So the ionization energy will be positive 0.85 and positive 4.25. So I should see a peak here at 0.85, and I should see a peak somewhere over here at 4.25. Exactly where you put them is not a big deal. okay? But I'm going to see 2 peaks. And what about the ratios? Well, for the 4.25 peak, there should be 2, and for the 0.85 peak, I should see 3. So this peak versus this peak is going to be 3 times as high. Well, not 3 times. If this peak was height 3, this peak is going to be height 2. So let me kind of come back for a second and just remind you that this is not ever shown on the machine. The machine doesn't know, oh, this is the 2 electron peak, this is the 3 electron peak. What the machine will do, what the computer will do, is it'll measure the height of this thing, and it'll say, oh, this peak is exactly 0.667 height. Like, it's a 2/3 of this height. And from those ratios, you can then figure out, oh, maybe it's the fact that there's 3 electrons in this peak, maybe there's 2 electrons in this peak. It could be 6 and 4, right? We don't know the exact number of electrons, but we know the ratio, okay? But if this is what the picture was, then that's how it would look. So this is a photoelectron spectroscopy spectrum. And what we're going to do now, well, not today, but on Wednesday, now that you can read them a little bit, understand what they kind of mean, we're going to look at various photoelectron spectra for these elements and see what new information we can find. Because I'm going to tell you this, the current shell model that we're using is still not good enough. There's a few things that it doesn't explain. So there must be a little bit more to it. And if you have taken high school chemistry, you might remember the S shell and the P shell and the D shell, all that stuff. That's what we're getting into next, okay? So where does that come from? Why is that a necessity for explaining electron configuration? Well, we're going to see why, okay? All right, that's it. You got questions on your exam, feel free to stay behind. If you want to talk to me about it, I'll be here. Otherwise, if you want a long talk, we can meet during lab or Thursday morning. My other long period of time is Monday morning, which was today already. Other than that, I'm kind of booked up, so you'll have to find me right before class or something. If you got homework to turn in, please bring it up. And that's it. So our quiz, again, on the energy level stuff, like the Bohr model of the atom. Stuff we haven't, that wasn't out on the exam.